Hello everyone, today let's take a look at Quantipus number 69, another conditional probability question. So suppose there's a test for HIV that is 99% accurate in both directions and 0.3% of the population is HIV positive. So if someone tests positive, what is the probability they actually have HIV? So let's just define our event so it's easier to write out. So I have HIV, that's the event that a person has HIV obviously, and the plus symbol will be the event that a person tests positive for HIV. So the question is asking us, if someone tests positive, what is the probability they have HIV? So they're asking us for the probability of someone having HIV given that they test positive. So let's let this box out here represent our population, and everyone either has HIV or they do not have HIV, right? So this completely partitions our sample space and there's no overlap. 0.3% of the population actually has HIV, so this is supposed to represent 0.3% of the population, so it's obviously not drawn to scale, right? And this side would represent 99.7%. Now it tells us the test is 99% accurate in both directions, so that just means that the probability of someone testing positive, given that they actually have HIV, is just equal to 99%, and the probability of someone testing negative, given that they don't have HIV, is also equal to 99%. So now let's draw the event that someone tests positive for HIV within our sample space. Again, this is not going to be drawn to scale. What the question's asking us, given that we're within this bubble here, what is the probability of HIV? So it's asking us to take this red portion and divide it by the orange portion. Obviously, we've done this before. And all that means in more formal terms is we're taking the probability of HIV intersection positive, right, the red part here, divided by the probability of positive, which is just the entirety of the orange circle. So let's do the red portion first, asking us what percentage of the population both has HIV and tested positive for HIV. So we know that 0.3% of the population actually has HIV, and of those 0.3% of people, 99% of them will actually test positive for it. If you wanted to write that more formally, that's just the probability of having HIV times the probability of testing positive given that you have HIV. So that's the red portion, but what's the entirety of the orange portion? Well, that's just going to be this red portion here plus this other side, the blue portion here. So this right here is the red portion. Now we need to add on the magnitude of the blue portion, and that's just going to be the intersection of the positive with the HIV complement event. So again, 99.7% of people do not have HIV, and of those 99.7% of people, we have exactly 1% of them that will actually test positive for it. This is just the probability of HIV complement, if you wanted to write it more formally, times the probability of having a positive test result given that you do not have HIV. So this is the magnitude of the blue portion over here, and when we plug that back in, right, we have the blue portion plus the red portion makes up the entirety of the orange portion, and now we have everything that we need to solve this. We have all the numbers, and when we do so, we're going to get 0.2295, so that's equal to about 22.95%. So given that you test positive, you only actually have HIV 22.95% of the time, which is obviously surprising, right? And the reason this number is so low, given that the test is 99% accurate, is just because the percentage of people who don't have HIV is so much higher than the percentage of those who do. For instance, imagine I had 100,000 people, right? Well, then 99.7% of them wouldn't have HIV, so we'd have 99,700 without HIV, and we'd have exactly 300 with HIV. And of the 300 people who do have HIV, we have 99% of them actually test positive. So 300 times 0.99 is going to give us 297 of these people actually test positive. And of the people who don't have HIV, 1% of them will actually test positive, right? So 1% of 99,700 is going to give us exactly 997. So you can see that most of the people who test positive don't actually have HIV, right? 997 is bigger than 297. And that's just because 1% of this number is going to be a lot bigger than 99% of this number. In this situation, we had 997 plus 297 people who actually tested positive, and of those people, only 297 of them actually had HIV. So this would also give us about 22.95%, which we expect, right?